Our next speaker is Aniket Joglekar. He will be talking about neutron star heating with inelastic dark matter.
Yeah, thanks for the invite. So I'll talk about this neutron star heating business, and in the end we'll show some interesting implications for inelastic dark matter type of models. So as we know, we need to probe what is the nature of the dark matter. So mainly we implement like these three types of strategies. Now typically when we think of any astro signatures for dark matter, like any compact object, what comes to mind is an indirect detection. But typically indirect detection at fundamental level is basically some DM annihilating to give you standard model particles. Neutron star heating is slightly different in the sense that it works similar to the direct detection, where dark matter scatters of a standard model, and so it's not an annihilation process. So the competing experiments on Earth would be the direct detection experiments, and they suffer from some drawbacks sometimes. They have done great work, but this is the status. So for like inelastic DM, where they can't supply enough energy, they can't deposit enough energy because there is not much energy to begin with. The velocity of dark matter approaching Earth is like 10 power minus 3. So at best you can do like a mass gap of 10 power minus 6 times the mass of the incoming dark matter. So there is a natural disadvantage there. Then if somehow dark matter only couples to leptons and not quarks, then also will be at disadvantage. So there are many such things where direct detection might have like a big blind spots. So people are looking at different stuff to cover for this, and lots of various avenues are being pursued. This is just some randomly picked interesting avenues. There are many more. This NOMA study nicely sums it up, whatever is the status so far. That is also now another 1 or 2 year old, so more stuff is coming out. I'll just stick to this first one, where neutron star kinetic heating, dark matter depositing into the its kinetic energy into the neutron stars. Okay, so some very basics, like why neutron stars? They are very dense objects, as a result of which we have a lot of targets, and also the gravity is very high. So the dark matter that is incoming can be accelerated to very high velocities. So whatever is approaching Earth is like 10 power minus 3. Here you get almost 0.6. Okay, so and number of targets is phenomenal, 10 power 57. We can't build such a large detector here. So for that, so the way this works is that neutron star is going around in halo. Dark matter comes in, hits one of the targets, loses some energy, and if it loses more energy than it had in the halo when it was at a very long distance, then we call it captured, because now it's gravitationally bound. If you just because it can't go back where it came from, it lost its energy. So it starts orbiting and then suffers multiple collisions one after another, and eventually thermalizes with the matter in the star. So that's the basic process. So how much is the flux then? So naively one would think like whatever is the geometric cross section of the star into the density and velocity will get us the flux. But here we have like a very strong gravitational field. So the impact parameter is actually quite big. Impact parameter almost goes to 10 power 3 times that of the radius of the star. So neutron star radii are like typically 10 kilometers. Here impact parameter can go 10 power 3 times that, which is a pretty big impact parameter. In fact, the impact parameter is comparable to other larger stars. It's slightly less still, but it's pretty big. So the neutron star, the dark matter capture in the neutron star doesn't suffer from the having a less flux compared to like capture in other astrophysical objects. So that's the main point here, and the factor can be easily calculated. Some kind of a angular momentum conservation type of thing. You can think it will come out roughly this factor. Okay, and this rough estimate is like 1,000. It's some like 800 or something like that. So so clearly on flux side it's slightly less but not too less, and on the density side it just is way above all other objects. Also, if the star is really old, it can have much lower temperature. So whatever neutron stars we have observed still are like thousands of Kelvin, like 40,000 Kelvin or whatever. But there is a possibility if we could find more old neutron stars, like more than billion-year-old neutron star, there is a chance that they might have cooled to much lesser temperature. So in that case, whatever the energy that is being deposited could end up heating it more than what is expected. So the steady state temperatures could be more than what cooling models would expect, and that's where we could have some short at detection. These other objects will have more temperature, so there is a less clear disadvantage if you want to detect the anomalous heat. There are other things people study in these also. Those are also the cross section. Because of this density, cross section that neutron stars can probe can go really low compared to other objects. So that's why the neutron stars are kind of interesting. Now, how does this kinetic heating exactly work? Some flux is coming in. Flux is roughly this much. Flux is roughly this much. So, and kinetic energy of each incoming particle is like a escape gamma minus 1 at surface, at least. Inside it will be slightly higher. At surface it is gamma minus 1 mx. So if you just multiply, you can come up with this formula for the flux, where F is the capture efficiency. So like not everything that comes in will be captured, only a fraction of it will capture, that will be the F. So from there you can just equate it to the radiation, assuming it as a black body. Doesn't have to be, it's like approximately it's okay assumption. So if you assume it to be a black body and equate it to your black body radiation, you get a steady state temperature, and the steady state temperature works out to be roughly this. So here the entire game is just calculating how much this F would be, and that would be the particle physics input to this temperature calculation. Once you calculate F, you directly have temperature. Now this is for non-annihilating. If it is annihilating, then in that case you can have even higher temperature, because you see the gamma escape is like roughly 1.3. So this is like 0.3 times mx. So without annihilation, only this much energy you are depositing per incoming particle. If it annihilates, almost all the mass energy also you can get. So almost 4 or 5 times energy you can total go into heating, and 1/4 power of that. So it will be roughly like 1.52 times, 1.5 times enhancement, I would rather say, in the temperature. So this 1600 might become like 2500. Okay, so that is the temperature. So in the end, but we still need to calculate F, and the procedure for that will be the same whether there is annihilation or not, no annihilation. So what's the game here? So hope is that some radio telescopes will detect nearby neutron star which are super old and have spun down enough and are expected to have very low temperatures, like order 100 kelvins. And then this heating mechanism, as I just now showed, if the F is 1, it can heat it up to about 2000 Kelvin, right? So there will be the anomalous heating. So if we can find such a star which theoretically in absence of dark matter heating should have been at like say 400 Kelvin, but now instead if you point your infrared telescopes to it, you are seeing 2000 Kelvin or 2500 Kelvin. Then in that case we can say it's anomalously heated, and maybe the reason is this. So this is the way we hope to detect such things. How much exposure we would need? The formula roughly is this, but in terms of actually detecting it, there could be some limitations also. So all the details of like how these technical details of how this imaging works and how much exposure is needed. So there are some additional papers that discuss this. So some of these limitations point out that maybe we need long enough exposures, or even with that we need temperatures more than like 2300 Kelvin, or but it's still achievable with if full annihilation advantage if we get. So all these caveats, I'll assume that we can hopefully detect anomalous heating this way. With that, now let's see what could be the implications. So first we need to compute F. So F computation, if the stuff inside is largely non-relativistic, we could just compute it with this simple formula, like just get a particle physics cross section from here, and this is the geometric cross section of the star. The ratio will be F. If ratio exceeds 1, then you take it 1, because then everything will be captured. So it's a pretty simple, straightforward formula. If stuff inside is moving very fast, ultra relativistically, and it can, because for example, the matter in the neutron star is highly degenerate. So there are electrons in the neutron star. About 5% of a neutron star is electrons. So electrons have Fermi energy of about 0.1, 0.2 GeV. You know, electron mass is 1 MeV, so we have pretty high, almost like very high velocity of these electrons. So they are ultra relativistic. In that case, such calculation fails, because they are going all around the place and you can't have this type of calculation. So you need little different formalism. Another complication there is that there is polyblocking, because again there is a matter is degenerate. So especially like again in case of so you need to, it's in momentum space, if the targets are sitting here, you need to, whatever the incoming dark matter is going to transfer the energy, it needs to knock it out of this sphere. And so not all energy transfers would result in the this type of energy deposition. So this also needs to be taken care of. So both needs to be taken care of inside. So we do that in our one of papers. So we build this, and also we need to take care of all the frames, which some quantities are computed in neutron star frame, some in computed in the center of mass frame, dark matter frame. So properly putting together, the easiest way to do it is using a molar velocity. So using molar velocity, we can just write down this type of formula, then which we can use to compute this F, which is the most important computation here. Several angles show up during this calculation. One is obvious, the scattering angle, but the other angle between the initial velocity of dark matter and the velocity of the target, these type of things show up. So we consider all this and compute the F. Now for concrete computation we need models. So two classes of models we consider, like one is like this type of EFT kind of approach, where you have an effective operator whose scale is much larger than the momentum transfer involved. So and the other one is like you have mediator mass and couplings, so you can put constraint on the couplings. How do the results look like? Since this formula is there, F will go with the cross section, and cross section is inversely proportional to 1 by lambda power 4. So temperature comes out to be inversely proportional to the lambda, because this 4 power 1 by 4 cancels. So you have this type of a curve. Now you can see these are the direct detection constraints, and the darker ones are the colored and darker ones are the neutron star constraints. So these upper ones are for dark matter that couples to both quarks and leptons. These lower ones are for the dark matter that only couples to leptons. So as you can see, for leptons it outperforms by a lot. For both it is comparable. In some places neutron stars can give a better constraint, some places the direct detection can give better constraints. Another thing to note is that the electron constraints are quite close to the neutron constraints, which gives the advantage in terms of detecting leptophilic dark matter, because for leptophilic the direct detection is very weak. So as you can see, it can cover wide mass range. Now in this region you will have some collider constraints, so this won't be always as free. There could be some ways, but this is largely constrained by colliders. But still you can cover wide mass range even for a higher side of the masses. As you go more than 1 PeV, it falls, because multi-scatter are required. For 1 PeV, the incoming energy that it needs, the halo energy is like, it's So in one go, it cannot deposit all its energy, whatever it had in halo, because a heavier particle had more energy in halo, so it can't do that. So you need multi-scatter. Whereas in this region you have poly-blocking, and also the cross section is declining because cross section goes as this formula. So you have a very sharp decline here as well in terms of the sensitivity. So these similar features will also appear when we do for inelastic. So this is so far for elastic dark matter. And then if we look at the other type of models with a mediator and coupling, the constraints on the coupling are basically inverted with the same type of dependencies on mx. Here also you can see, like, these are only for leptophilic dark matter, it outperforms. For one that couples to everything, it's sort of comparable in both sense. So now coming to inelastic dark matter. Inelastic dark matter is important class of models where especially the in context of SIDM has been talked about, and also for a sub GeV kind of dark matter, it's a very good model to have because it can alleviate some of the cosmological problems otherwise suffered by it. So that's why we consider inelastic dark matter models. There basically what you have is two states of dark matter split by a small splitting. Let's call it small delta m, and capital delta is the ratio of these two, where m1 is the lower mass state. In that case, in neutron star, because of very high gravity, we have very high velocities. So there is a chance that kinematically we can jump this gap for the scattering to happen, which is not always the case when there is a direct detection involved. So if you work out analytically and approximately, of course, because otherwise the formulas are very complicated, the maximum mass gap that we can jump in a neutron star setting comes out to be about these formulas. So these first ones are very easy to see. It's just the total energy that can be deposited. The other two ones need a full relativistic formalism again, so it's not very straightforward. The final formula, first order approximation, comes out very simple, but it's a bit involved computation. So as you can see, the same plot that I showed for the elastic, but now it's sharply cut off here, because here it's suddenly the kinematics stops working. It can't jump the gap while scattering. Now it might be a bit counterintuitive as you go to higher masses why it can't jump. Well, because this delta is being fixed, not delta m, delta is being fixed, which is the ratio. So the delta m blows up with mass. So that's why it looks a bit counterintuitive, but it's no problem. Important thing is that again, this is for leptophilic and this is for something that couples to both. And again, these come out very close. Again, the reason being, the Fermi energy of electrons and the mass of the neutrons are not that far, less than an order of magnitude separated. So that's why they are close, and this is the main advantage we have in this case. So now we consider a more concrete model. This is a very classic benchmark model for inelastic dark matter. You have a dark photon, two states only off diagonally coupling to it, and the standard model coupling with the suppression of epsilon factor. This is a standard dark photon model, and here you can see, so like this dark gray are what are the current terrestrial constraints on it. These are not the direct detection constraints, these are the high intensity frontier and beam dump constraints and fixed target beam dump. So these red lines are the thermal relics for this particular so if dark photon mass is 3 times the lighter state, this is the red line part is of parameter space, is what is compliant with the relic density and thermal relic. Similarly for this another values. Why these values? Because this is the region that's most cosmologically viable region. If you go too high or too low, you run into a lot of problems. So as you can see, again, the regions for electrons and neutron scatterings are comparable, whereas the earth bounds are slightly weaker in this case. Here is where it really, so as you can see in the slide before, the delta is 0.1, which is pretty high, which is good for the beam dump and this LLP type of searches. Having a higher delta gives you more boosted states, whereas for direct detection you want low delta. What neutron star really outperforms, if this could be worked out, it will really outperform for the in-between delta, where both have disadvantage. So these in-between deltas, it gets even better. So if I reduce the delta a bit, so this delta is low for this collider and LLP and these type of searches, but it's too high for the direct detection. And as you can see, the field gets more clearer here, right? This is a second type where the mass of the mediator is lower than the mass of the lighter state. Cosmologically again problematic, but if one can build cosmologically viable models, then again this is the region where a lot of papers are written about probing this region. This region can be potentially probed with neutron star. Accelerator constraints are like again mix of all those constraints. I have probably been lazy to not put the names exactly which experiment where. So I'll leave you with the summary, and yeah, so they can basically, this message is same. There are complementaries, these are complementary, could be complementary searches which can outperform in certain important parameter space regions. Yeah.
Okay, thanks for the nice talk, and any question, comments? They hand raised their hand.
Thank you so much for the talk. It's a very nice question. Naive question I want to ask. I think is that people explore this dark matter density spike around black hole, right? Dark matter density spike. So, I mean, which can enhance the signal, like annihilating signal. So, is there any possibility that one can also talk about this kind of spikes around the neutron star?
Maybe I have not explored it, sorry.
Okay.
Yeah.
Okay. So it's not that nice question.
So just curious, so you have used this very anomalously high temperature neutron star as a proxy to detect the interaction, right?
Yes.
So would that also affect the mass radius relation of neutron star, like during the collapse of star?
No, not really, because the amount of dark matter you are collecting is still very low.
Okay.
So for mass radius relation equation of state, like
that won't get affected.
No,
like at least the parameter space that you have.
Total matter you have is like so you can estimate the flux is roughly, so for 1 GeV mass, the flux is roughly 10 power 42 particles in the total billion years lifetime of the star.
Okay.
For 1 GeV. The higher the mass, so the 10 GeV mass, it will be 10 power 41, 100 GeV will be 10 power, and so on. Whatever it is, even if you get like 1 keV, that would bump it to 10 power 47. The total mass you will still capture is about 10 power 42 GeV. And mass of the neutron star is 10 power 57 GeV.
Mm-hmm.
So it's always like 1,000 trillion times less stuff. So in terms of density profiles and all, it doesn't.
But what about the cooling mechanism that can change the kind of an equilibrium that a neutron star will come up?
Correct. But it only will come into effect at a late time, right? Because the temperature, whatever the cooling models predict, this is based upon the cooling. At least till 10 or 100 million years, the neutron star is still quite hot, like some 40,000, 50,000 Kelvin, 100,000 Kelvin. So that time this energy deposition is not in play anyways. It's later time close to billion, hopefully. I mean, we don't have anything, any data as such as extrapolation. If it works out, then that time then this thing starts interfering with it, because then it will set up a steady state at 2000 Kelvin or something like that.
I see. Okay. Thank you.
Yeah, sorry, I think what about evaporation?
Yeah, so evaporation will matter, and there have been studies on evaporation also, but in this case, I mean, evaporation really matters when the dark matter mass is really really small, right? So in the evaporation from what? Sorry, okay, let me ask this. Evaporation of, so there is a one way to evaporate, but that is because I think it's below keV the evaporation will matter more. At least the evaporation that I'm thinking of, unless you have some specific evaporation in mind. Just because of this, the distribution of targets, thermal distribution of target, that comes into play below keV, not below GeV. So yeah, we went a little overboard in this plot going below keV, but above keV it should be okay, I think, evaporation. keV, that's what I said. keV or maybe 10 keV.
And further than that, Raghu can answer this better.
He has the thing on the evaporation side.
Escape energy over the temperature of the body is order to the very capacity. So escape energy over the temperature for neutron star. Escape energy is very high and temperature is low. Basically, you solve for the mass by keeping the right hand side 30. It comes out keV for electron volt masses.
keV is safe. Pushing it, you can go -7 or something also, I guess. No,
So it depends on the temperature.
Yeah, but keV or 10 keV is very safe. Above that is safe. So.
Okay, so let's finish the session and thanks again.